Hello, everyone. How are you going? For today, we are going to discuss algorithm complexity. For any defined problem, there can be a number of solutions. This is actually true in general. Like if you want, you can be called as a master chef if you can cook eggs in many different ways. You can have egg omelette, sunny side up, scrambled egg, or a boiled egg. In a similar manner, you can also be called as a programmer if you can provide many solutions to a certain problem. As I've said, there are often many approaches or algorithms to solve a problem. How do we choose between them? At the heart of computer program design, there are actually two goals which are sometimes conflicting with each other. Number one is to design an algorithm that is understand, code, and debug. While the second one is algorithm that makes efficient use of computers resources. So the goal one is focused on software engineering, while the second one is concerned about data structure analysis and algorithm analysis. When goal two is actually important, how do we measure an algorithm cost? So this is what this topic is about. Specifically, we get to explain the importance of efficiency. Second one is to discuss the underlying concepts about space and time complexity in evaluating program performance. For example, you have here two integers, num1 and num2, and you want to find the sum of these two numbers. How will you solve this? One possible solution for this kind of problem is actually to take two integers as an input, create a variable sum of to store the sum of two integers. You put the sum of those two variables in the sum variable and then return the sum variable. In the given example, you will find three things here: the input, the algorithm, and the output. Both data structures and algorithms are actually needed to solve computer science problems. Algorithm talks about the way to solving a problem, while data structures is organizing and managing the data using which we are solving the problem. Algorithms are like verbs, and the data structures are like nouns. According to OMSI, an algorithm is just a method of doing something on a computer, while a data structure is a layout for memory that represents some sort of data. Now let's talk about the how do we measure the program's efficiency. So the efficiency of an algorithm is mainly defined by two factors. We have the time complexity phase. It is said to be that a good algorithm is one that is taking less time and less space. But it's not always the case, or it's not possible all the time, because there is a trade-off between the time and the space. If you want to reduce the time, then space might increase. Similarly, if you want to reduce the space, then the time may increase. So you will have to compromise with either the space and its time complexity. Now let's get to learn them one by one. So let's focus on the space complexity of an algorithm denotes the total space used or needed by the algorithm for various inputs. As you can see in our example, we are creating an array of size maps. Hence, the space complexity is in the order of max. Max will increase, the space requirement will also increase accordingly. Even when you are creating a variable, then you need some space for your algorithm to run. All the space required for the algorithm is collectively called space complexity of an algorithm. Note that in normal programming, you will be allowed to use 256 MB of space for a particular problem. So you can create an array of size up to 10 raised to the power of 8. Also, you can create an array of size more than 10 raised to the power of 6, which is actually equivalent to 4 MB size. So to use an array of more size, you can actually create or declare that array into a global array. So whenever a solution to a problem is written, some memory is required and may be used for the following. Number one, variables. This includes the constant values and temporary values, the program, which is talks about the procedures, and then the execution, which is during the running of the program. So sometimes auxiliary space is confused with space complex, but auxiliary space is the extra space or the temporary space used by the algorithm during its execution. While executing, algorithm uses memory space for three. Number one is instruction space. It's the amount of memory used to solve the compiled version of instructions. The second one is environmental stack. Sometimes an algorithm or a function is maybe called inside another algorithm. During this situation, the current variables are actually pushed into the stack or the system stack, where they wait for further execution and then the call to the inside algorithm actually means. For example, you have here a function which is called process, calls function input inside it. Then all the variables of the function process will get to stored in the on the system stack rather temporarily, while the function input is called and executed inside the function process is done. Now, another third one is data space. It's the amount of space used by the variables and constant. Actually, when we talk about space complexity of any algorithm, we actually consider data space. We neglect the instruction space and then the environment. So how do we calculate the space complexity? For calculating the space complexity, we need to know the values of memory used by different data types or the variable that we are using. Uh, According to a specific data type, which generally varies on or for different operating system or a platform. But the method for calculating the space complexity remains the same. So as you can see here in our matrix, we have data type, and and beside it is the corresponding size. So for byte and boolean, we have 1 byte, and then we have 2 bytes for short and car, and then for int is we have 4 bytes, and long double are 8 bytes respectively. Now let's learn how to compute space complexity by taking a few examples. As you can see in in our program, you have here variables num1, num2, and sum, which are integer types. Hence, they will take 4 bytes each. So total memory requirement will be 4 times 3 plus 4, which is equivalent to 16 bytes. The additional 4 bytes is actually for return value. And because this space requirement is fixed, this is called constant space. Let's have another example here. You can see in our function, we have an array R and a max arguments. So this kind of program will actually will actually calculate the sum of the elements of an array based on the max. So therefore, 4 times max bytes of space is actually required for the array elements, while 4 bytes each for our max and sum in the return value, including the I. So therefore, the total memory required will be 4n plus 12, which is increasing linearly with the increase in the input of value or input of max or value of max. And then we can actually call this as linear space complexity because as it increases linearly, based on the increase of size max accordingly. So similarly, we have actually quadratic and other complex space complexity as well. As complexity of an algorithm increases, but we should always focus on writing algorithm code in such a way that we keep the space complexity minimum. And this quadratic algorithm or complex space complexity that I've said will be actually discussed in algorithm analysis course in your higher year. The time, let's talk about time complexity. So the time complexity is the number of operation algorithm performs to complete its task with respect to the input size, considering that each operation takes the same amount of time. The algorithm that performs the task in the smallest number of operation is considered the most efficient. So uh, here we have the input size. Input size is actually defined as the total number of elements present in the input. For a given problem, we characterize the input size and appropriately. For example, in the sorting problem, we get to uh, we need to get the total number of items to be sorted. For a graph, we have the number of edges and vertices. For numerical problems, here the total number of bits to represent a number. So the time taken by an algorithm also depends on the complex computing speed of our computer or system that the computer we are using, but we ignore those external factors, and we are only concerned on the number of times a particular statement is actually being executed with respect to the input size. So let's say for executing one statement, the time taken is 1 second, and then what is the time for executing n statement? It will actually take n seconds. Suppose you are having one problem and you wrote three algorithms for the same problem. Now you need to choose one of uh, those three algorithms. So how will you do that? First is you can do this. You can actually one thing that you can actually do is just to run all the three algorithms on three different computers. Provide the same input and find the time taken by all the three algorithms and get to choose one that is taking the least amount of time. So is it okay? Probably no, because all the system might be using more some different processors. So the processing speed might vary. So we can use this approach to find the most efficient algorithm. Another thing that you can actually do is you can run all the three algorithms uh, probably on the same computer and try to find the time taken by the algorithm and choose the best one. But here also, you might get wrong results because at the time of execution of a program, there are other things that are executing along with your program, like MS Word, Eclipse, Photoshop, like browser such as Google Chrome. So you might get the wrong time. So one thing that is to be noted here is um, that we are finding the time taken by different algorithms for the same input size. Because if we change the input, then the efficient algorithm might take more time as compared to the less efficient one because the input size is different for both algorithms. So we have seen that we can judge an algorithm by calculating the time taken during its execution in a particular program or system. So we need some standard notation to analyze the problem of or analyze the algorithm. We can actually use the asymptotic notation, which is asymptotic notation is used to analyze any algorithm and based on what we find the most efficient algorithm. So in asymptotic notation, we do not consider the system configuration. Rather, we consider the order of growth of the input size. We try to find how the time or how the space taken by the algorithm as it increases or decreases after increasing and decreasing the input size, which actually we talk about it on the next chapter. So Now, let's focus on the time complexity. As what I've said earlier, there can be n solution for every problem. When I was still in college, after our class, I used to like compare my solution to my classmate, especially those who were good in programming, to see how they created an algo for the given problem. And whether I like it or not, we had actually difference. Usually, one who had the long lines of codes was always appreciated. But as I went through, I was able to find out that the number of lines of codes in a program doesn't seem to matter. In fact, I have read this in one of the books that I have read. Uh, the lesser the code, the better. Aside from you made not to consume so much memory space, it is believed that you were able to simplify complex solutions. So let's take simple example here. So we have here two examples for getting the sum of first and natural numbers. In the first program, we have here a it uses a loop where the loop iterate and based on the n times 1 plus 2 plus 3 until the max. And then the one is actually, or the second solution is actually a formula for getting the natural number, which is not n times the n plus 1 divided by 2. So basically, these two algorithms are different in a way they are written, but they actually target, or they actually it's like it's expected to have the same output, which is arriving the sum of the first n natural numbers. So you can see here, if I get to choose which one is the best solution for me, of course I will prefer the this one, no, the second one, which is by calculating or using the mathematical formula and calculating the first natural numbers from 1 to n or 1 to max, because of course it's constant. So what do you mean by like constant? Like it's the better approach of it as a program or as a solution, because there is it will only be executed once, and it will always be it does not require certain amount of iterations, just like what we have here in our uh, first solution, which is of course your memory will get to process it compared to the second one. Okay. So again, I'm going to reiterate. In the first solution, the time complexity will be n, at least. There is an increase of time taken as the value of n increases. While in the second, time complexity is constant, as I've said. It will always give the result in one step, because it is not dependent to an n or max value. And since the algorithm's performance may vary with different types of input data, hence for an algorithm, we usually use the worst case time complexity of an algorithm, because that is the maximum time taken for in any input size, which is that will be our focus in the next topic. So, as a summary of our topic for today, the efficiency of an algorithm is mainly defined by two factors: the time and complexity and space. Complexity, while executing an algorithm uses memory space for three reasons: the instruction space, environmental stack, and data space. The time complexity is the number of operations an algorithm performs to complete its task with respect to input size. The algorithm that performs the task in the smallest number of operations considered the most efficient. So again, input size is defined as the total number of elements present in the input. Now, so I guess that would be all for today. Thank you guys for listening, and have a great day. This is Marcel Baste, your professor for this. Bye bye. Thank you guys.